This class is an introduction to OAuth and OpenID Connect. In this class, we will learn about these important protocols for authorization and authentication that are crucial to pretty much a lot of web applications currently in use. Over the course of this class, we will provide a comprehensive overview of OAuth 2.0 and OpenID Connect. These protocols allow secure access to resources and user information on the web. In the first 5 lectures, we will cover the basics of OAuth and OpenID Connect, including authorization methods, tokens, and client registration. OAuth 2.0 is a delegation framework that allows access to user resources without exposing credentials. It involves interaction between clients, resource owners, authorization servers, and protected resources. Access is granted using access tokens. The OpenID Connect builds on top of OAuth 2.0 to enable clients to verify user identity. It uses ID tokens to represent an authenticated user identity. We will explore various OAuth 2.0 authorization methods, including authorization code grant, implicit grant, resource owner credential, and client credential. We will also understand bearer tokens, which are a type of OAuth access tokens that can be used by anyone in possession of it. We will discuss security consideration for bearer tokens. We will also discuss refresh tokens, which are tokens that allows renewal of access without re-authenticating. They have a longer lifespan than access tokens and can be revoked. We will also understand client registration and how does the client with the applications register, what happens when they register to the authorization server. We will cover confidential versus public applications and client profiles like web and native applications. OAuth and OpenID Connect are 2 vital protocols in today's digital network. The OAuth and OpenID Connect are aiming to simplify and secure user authentication and authorization process. They enable users to access applications and services without exposing their credentials. Instead of having the user provide their credentials, the actual authentication happens using secure tokens. In this slide, we are introducing the crucial need for such protocol in our interconnected online environment. OAuth and OpenID Connect are essential because they provide a standardized and secure way for applications to request and receive permissions to access user resources. They ensure that user credentials are not shared directly with third-party applications. This would reduce the risk for credential theft and enhance overall security. The third-party applications often require access to resources owned by end users. This is resources that might have personal data, such as their personal data or functionalities within other services. OAuth and OpenID Connect facilitate this access in a secure manner, ensuring that end users' permissions are obtained before any access is granted. Application delegation refers to the process of granting a third-party application limited access to user resources without actually exposing the user's credential. OAuth and OpenID Connect play a crucial role in this by providing secure tokens to applications once the user's permission has been obtained. The exposure of user credential poses a significant security risk, making them susceptible to theft and unauthorized access. OAuth and OpenID Connect mitigate these risks by eliminating the need for applications to store user credentials, instead using secure tokens for authentication. Here's some definitions relating to this topic. A resource owner, this is the user who owns the resource being accessed. A resource server, This is the server where the user's resources are stored. It could be like a shared drive or Google Drive or something like that. Client, this is a third-party client application requesting access to the user resource. And the authorization server here was which I'm referring to as Google logo. This is the server that authenticates the user and issues access tokens to the client. The authorization server, this is the server that authenticates the user and issue access token to the client. The OAuth and OpenID Connect flow begins when the client requests authorization from the user to access their resources that they own. This is a crucial step in ensuring that the user is aware of and consents to the access being granted. The user then authenticates with the authorization server, providing their credential directly to the trusted authorization server, which could be Google or Microsoft or anything like that. This is a trusted entity and not to the third-party application. They're not providing this to the third-party application. Upon successful authentication and authorization, the user is redirected back to the client application. The authorization server provides an authorization code to the client application, signaling that the user has granted access that is needed. The client sends the authorization code back to the authorization server to request an access token. The authorization code is exchanged for an access token, which will be used to access the user-protected resources. Finally, the client uses the access token to access the user's protected resources on the resource server. So what gets exchanged between the client and the user, which in the past required the client to have the user name and password or the credentials for the user, now it's just going to be exchanging an authentication grant for an access token. And this is what the OpenID Connect and OAuth is achieving, is that the user credentials are no longer shared to the third-party applications, which is referred to in the standard of OAuth and OpenID Connect as client. This is the client that's a third-party client that's trying to access resources owned by a resource user. So protected resources by a resource user. In the past, this would have required the user to share their credentials with the client. Now, all they need to do is provide authorization to the authorization server, and the authorization server exchanges a grant, and that grant gets exchanged with an access token. In this lecture, we will discuss the authorization methods for OAuth. There are different methods for granting third-party resources access to users' own resources. One of those methods is authorization code, which grants the user authorizes the client via browser, and the client gets a code and exchanges it for a token. That's one method. The implicit grant method, user authorizes client via browser, and client gets the token directly. And then the other method is resource owner password grant, which users gives credential to client, and client gets token with the credentials. And then finally, the client credential grant, in which the client gets the token with its own credential. In authorization code grant, this is the most common method and is recommended. It involves a user agent, such as a web browser, that redirects the user to the authorization server. The user gets redirected to the authorization server, where the user can authorize the client application to access the protected resource. Usually this includes asking the user for, what exactly they would like to authorize for access. The authorization server then returns an authorization code to the user agent, the browser, which passes it back to the client. The client then exchanges the authorization code for an access token, the token endpoint in the authorization server. This method is secure and flexible as it allows the client to obtain the access token without exposing it to the user agent or the resource owner. And also it supports the refresh token in multiple scopes as well, which we'll discuss. This diagram shows the steps involved in the authorization code grant, where the user authorizes the client to access a protected resource on their behalf, and the client obtains an access token from the authorization server. The client can then use that access token to request the protected resource from the resource server. Let's take an example. Alice is a user of a web app called Bookstore, which allows her to browse and buy books. She can buy those books online. The bookstore uses an external service like PayPal, for example, to process the payments for the books. Bob is a developer of the Bookstore app. He has registered his app with PayPal as a client. He has obtained a client ID and a client secret from PayPal, which he uses to identify his application to the authorization server. Now, Alice wants to buy a book on the bookstore, but she needs to authorize the application to access her PayPal account first. So what happens is she will click on the pay button on the bookstore, which redirects her to the authorization server of PayPal with the client ID and scope, which basically identify Bob. And scope would be something like pay. Redirect URI would be the redirect place where she needs to go. The authorization server authenticates Alice via her browser, and you've probably done this multiple times. And the browser would ask her to grant or deny access request from the bookstore. Alice then grants the access, and the authorization server redirect her back to the bookstore. And now the bookstore redirect back would be with the URI provided. The redirect URI includes an authorization code and a state in the query string to indicate the state of the authorization process. And we will kind of dive deeper into those things in a little bit. The bookstore extracts the authorization code from the query string and exchanges it for an access token from the authorization server of PayPal. It's getting this using its client ID and client secrets, which is basically the logon information for that application. The authorization server verifies the code and the credentials of the bookstore app to ensure it's valid, and then it's going to return an access token to the bookstore app. The bookstore app would then use the access token to request the payment for the book from the resource server, which is PayPal. So the resource server verifies the access token and processes the payment for the books purchased in the bookstore. Bookstore confirmed the payment to Alice and thanked her for doing business. So it's kind of an example of authorization code, which you've probably seen a lot. Now let's take a look at the implicit grant. Implicit grant is a simplified version of the authorization code process, where the authorization server directly returns an access token to the user agent after the user authorizes the client. This method is less secure and less flexible as it exposes the access token to the user agent and the resource owner, and does not support refresh token or multiple scopes. In this method, it's mainly just used for client-side web applications that run in a browser. The steps involved in the implicit grant flow is the user signs in and consents to the client application to access protected resource on their behalf, and the authorization server returns an access token directly to the client. The client can then use the access token to request the protected resource from the resource server. As an example, let's say Eve is a user of a web app. We'll call this music app, which allows her to listen to and share music with her friends. The music app uses an external service called Music App API to stream the music from various sources. Frank is the developer of the music app, and he has registered his app with Music API as a client. He has obtained a client ID from Music API, which he uses to identify his app to the authorization server. Eve wants to listen to a song on the music app, but she needs to sign in and consent to the app to access her music API account first. She clicks on the sign in button on music app, which redirects her to the authorization server of music API with the client ID and scope. Scope would be something like play. Play as state would be another parameter that's passed, and redirects URI as parameter. The authorization server authenticates Eve via her browser and asks her to grant and deny the access request from the music app. Eve grants the access, and the authorization server redirects her back to the music app using the redirect URI provided earlier. The redirect URI includes the access token and state in the URI fragment. The music app extracts the access token from the URI fragment and stores it in the browser local storage. It then uses the access token to request the song from the resource server of Music API. The resource server verifies the access token and returns the song, and it streams this song to the music app. Eve can now listen to the song on music app and share it with her friends. She can also revoke the access token at any time from her music API account if she wants to stop music app from accessing her music. Now, this is an example. The issue with this example with the implicit grant is the access token is actually present in the browser. The access token is going to be stored in Eve's browser, and anybody that compromises the Eve's browser will be able to access that access token, which means they would be able to access her account in Music API, because the Music app basically redirect the user back with an access token and a fragment. And also, in that case, the Music app has an access token that can easily be shared with any other, compromised and shared with any other resource that's needing access. So you can't really control the actual scope and of that access token. The next example is the resource owner password credential. The resource owner password credential grant the resource owner directly by providing their username and password to the client, which then uses them to obtain an access token from the authorization server. This method obviously is less secure, and it's not recommended as it requires the resource owner to trust the client with the credentials, and it does not support user consent or third-party authorization. It is mainly used for trusted clients that have a high degree of control over the resource owner's device, such as native applications or script. So example of this, as an example, let's say Alice is a user of a mobile app called PhotoShare, which allows her to upload and share photos with her friends. PhotoShare uses an external service called cloud storage to store the photo on the cloud. Bob is a developer of PhotoShare, and he has registered his app with cloud storage as a client. He has obtained a client ID and a client secret from cloud storage, which he uses to identify his app to the authorization server. Alice wants to upload a photo to the PhotoShare, but she needs to authorize the app to access her cloud storage account first. She enters her cloud storage username and password in the PhotoShare app, which then sends them along with the client ID and client secret, as well as scope, which is in this case would be kind of upload as a hypothetical to the authorization server of cloud storage. The authorization server verifies the credential of Alice and PhotoShare, and if valid, returns an access token and optionally a refresh token to PhotoShare. PhotoShare then uses the access token to upload the photo to Alice's cloud storage account. Alice can now see her photo on PhotoShare and share it with her friends. She can also revoke the access token at any time from the cloud storage account settings if she wants to stop PhotoShare from accessing her photos. But the problem is PhotoShare now have access to the Alice username and password, which is not which is obviously not a good way of doing things. But the client credential grant, this is a method where the client uses its own credential, such as client ID and secret, to obtain an access token from an authorization server. This method does not involve any user interaction. It's really a back-end authentication of the client to gain access to its own resources. It's mainly used to access resources that belong to the client itself or that are shared among multiple clients. As an example of client grant, Charlie is an owner of a web app called Weather App, which provides weather forecasts and alerts to its users. Weather App uses an external service called Weather API to get the weather data from various sources. David is the developer of Weather App, and he has registered his app with Weather API as a client. He has obtained the client ID and a client secret from Weather API, which he uses to identify his app to the authorization server. He has obtained a client ID and a client secret from Weather API, which he uses to identify his app to the authorization server. Weather App needs to update its weather data every hour, so it requests an access token from the authorization server of Weather API using its client ID and client secret and scope. For example, it could be read: the authorization server verify the credential of Weather App, and if valid, returns an access token and optionally a refresh token, which we will understand why the refresh token is important. This would be returned to Weather App. Weather App then uses the access token to get the weather data from the resource server of Weather API. Weather App can now display the updated weather data to its users and send them alerts if necessary. It can also refresh the access token periodically using the same refresh token, and this is a way of providing constant automatic refresh of tokens without going back to the authorization process one more time. We will discuss more in the next lecture. In this lecture, we will discuss bearer tokens. What are they and what are the security risks associated with them? Bearer tokens are a type of access tokens that are used in OAuth 2.0, a framework for authorization and delegation of access to protected resources. Bearer tokens are simple and convenient, but they also pose some security challenges and threats to security and privacy of users and applications. In this lecture, we will explore the concept of bearer tokens for OAuth 2.0, how they work, and what are the best practices and recommendations for using them securely. We will also look at some examples of common attacks and vulnerabilities that affect bearer tokens and how to prevent or mitigate them. I'm hoping by the end of this lecture, you will have a better understanding of bearer tokens, their benefits and drawbacks. OAuth enables clients to access protected resources by obtaining an access token, which is a string representing an access authorization issued to the client. And the client here, I mean the application, rather than using the resource owner's credential directly, which is resource owner is the end user. Tokens are issued to clients by the authorization server with the approval of the end user or the resource owner. The client or application uses the access token to access the protected resource hosted by the resource server that belongs to the end user. The bearer token is a type of access token that can be used by anyone that possesses it without proving the possession of a cryptographic key. A bearer token is a credential that represents the authorization granted by the resource owner, the end user, to the application or to the client. A bearer token can be used to access the protected resource at the resource server by sending it in an HTTP request, such as in the authorization header field or in the URI query parameter. And this shows how a bearer token is used to access a protected resource at the resource server by the client on behalf of the user. The bearer token is obtained from the authorization server by the client using its own credentials and the scope of access. The bearer token is then sent in an HTTP request to the resource server. In the authorization header field, the resource server validates the bearer token with the authorization server. It returns the protected resource or an error message depending on the validation results with the authorization server. The client then would display the protected resource because it would gain access to the resource if the authorization server validates the token, and it could return an error message to the user. When sending the access token in the HTTP request entity body, the client adds the access token to the request body using the access token parameter. This is either a post or get message depending on the implementation. The resource server validates the bearer token with the authorization server. It then returns the resource requested by the client. If the validation is successful, then client gets access to the resource. If not, then they get access denied. This shows you an example on what it looks like as far as the request content token is passed to the body. The body is in the form of form encoded URL, and the content type would be XWWW for form URL encoded and the access token in the body. In this example here, the resource server gets a request with no credential. So in this case, if the resource server gets a request with no credentials, or the credentials are not authorized, the resource server would return a 401 unauthorized status code and a www authenticate header field that indicates the required authentication scheme and parameters. And here, for example, we're saying the bearer, it will let the client know or the application know that in order for you to gain authorization, you need to be authenticated with the bearer realm, which could be, indication with which authorization server is the realm belong to, and then the scope or the authorization that needs to be allowed in the scope of the authorization server. In this example, read or write. The client does not provide any credentials. In this case, the client didn't provide any credential, and as a result, they get a failed to access resource and telling them, hey, you need to be authenticated with this realm. When this occurs, the resource server lets the client know the scope attribute required of the access token for accessing the protected resource. Example here is the resource server returns a 401 unauthorized status code and a www authenticate header field that indicates the required authentication scheme and parameters. The realm lets the client know what authorization server is meant by the request. The scope attribute is a space-delimited list of case-sensitive scope values indicating the required scope of the access token for accessing the requested resource. In this case, the client needs the access token with the read and write scope to access the resource. If the token was provided but it expired or no longer valid, the resource server can return the error. For example, here it says invalid token. So the www-authenticate is only sent by the resource server if the client access was denied. What gets sent in the response when the client provided an incorrect access token is the error describing what happened, which in this case would be, in this example here, the access token have expired. An attacker may generate a bogus token or modify the token content, such as the authentication or attribute statements of an existing token is modified, causing the resource server to grant inappropriate access to the client. For example, an attacker may modify the token to extend the validity period. A malicious client may modify the assertion to gain access to information that they should not have been able to view. In this example, Alice sent an access token to Bob, and there is Bob here could be the application. There's an entity that intercepts the request, the access token, and it would send it to the resource server, and inadvertently the resource server provides access to the interceptor to the resource. A malicious client register a redirect URI, also another token redirect as a threat. A malicious client registers redirect URI that points to an open redirector, such as in this example here, example.com authorized response type code, and the client is an open redirect. An example here, we're redirecting to, and this is where the redirect URI would text the user to parameter that can be used to specify any destination URL. The malicious client initiates an authorization request to the authorization server using the authorization code grant type and the registered redirect URI, such as it looks like this. The authorization server authenticate the resource owner via the browser and ask them to grant or deny the access request from the malicious client. The malicious client is kind of posing to be what it claims to be. The resource owner grants access without verifying, and the authorization server redirects them back to the malicious client using the redirect URI. The redirect URI includes an authorization code and state in the query, such as the client would gain access the resource to the resource that the user didn't intend to give him access to. This is also another risk. The malicious client then extracts the authorization code from the query string, exchanges it for an access token at the token endpoint of the authorization server using its client ID and client secret and redirect URI as a parameter. The authorization server verifies the code and the credential of the malicious client, and if valid, returns an access token, and optionally a refresh token, which we didn't talk about the refresh token, but we'll talk about it in a little bit, to the malicious client. The malicious client can then use the access token to access the protected resources at the resource server on behalf of the resource owner, the end user, without their consent or knowledge. It kind of basically tricked the user by redirecting them to what it seems to be something legit, but it's not. This would show you the malicious client uses an open redirector to exfiltrate an authorization code from the resource owner browser, and then it uses it to obtain an access token from the authorization server. The authorization client can then use that access token to access the protected resource at the resource server on behalf of the resource owner. And this threat actually happened very frequently, and it relies on kind of tricking the end user. Another threat is a token replay. In this case, a malicious client intercepts an access token that was issued to a legitimate application or client by the authorization server. This can be done by capturing the traffic using a network sniffer or a compromised proxy or an SSL decryption device. The malicious client uses that stolen access token to access the protected resource at the resource server, pretending to be the legitimate client. The resource server validates the access token with the authorization server and grants access to the protected resource, completely unaware that the access token was replayed by the malicious client. To prevent token redirect, the authorization server should include the identity of the intended recipient, the audience. We hear about the audience in multiple places down as we progress in the topic, and in the token, such as the URI of the resource server or a unique identifier. This is kind of let the resource server know who's the intended audience. In this case, the audience and the scope. Additionally, the authorization server should restrict the use of the token to a specific scope. It could be read-only or write-only access, and the resource server should check that the token scope is sufficient for the requested operation. In this example, Eve request was rejected because the scope and audience did not match. The access token that Eve intercepted was issued for the photo resource server with the scope of read, which means it can only be used to access photos with read permission. Eve cannot just copy the scope and audience as well, because the access token is a cryptographically signed string that contains information about the client, the resource owner, the authorization server, the scope and the audience, and other parameters. And believe it or not, this was a recent result, a vulnerability in Microsoft. The access token is signed by the authorization server using a secret key that only the authorization server and the resource server knows. If Eve tries to modify any part of the access token, such as changing the scope or the audience, she will invalidate the signature and make the token unusable. The resource server will then detect the tampered token and reject it. Also, another things to keep in mind is the scope and audience are stored by the authorization server in its persistent storage and are used to check if the token is valid and authorized for a specific resource. The resource server needs to call the authorization server to validate the token and obtain the scope and audience information. Another thing to keep in mind, something important, the authorization server does not send the scope and audience to the resource server. It is sent by the client or application and confirmed by the resource server. So the two have to match, meaning that the information coming in from the resource owner and the resource server, two different parties, they have to match. The client requests an access token from the authorization server with a specific scope and audience, which indicates the intended use of the token. The authorization server issues the token with the requested scope and audience, or rejects the request if it's invalid or unauthorized. The client then sends the token to the resource server to access a protected resource. The resource server validates the token with the authorization server and obtains the scope and audience. The two have to match. The authorization server provides the resource server the authentication, the audience and scope. So this is also another safety measure. It's very critical that the audience and the scope parameters are used to request and validate the access token, but they're not a part of the access token itself. Nonces are random strings that are used to prevent token replay. They prevent token replay attacks by ensuring that each request is unique and cannot be reused. This is done using a number used once, a nonce. The nonce is generated by the client, the application, and sent along with the access token and other parameters in a MAC header, message authentication code, which is a hash. The resource server validates the nonce by checking it against the asymmetric public key of the sender. So it's using cryptographic functions like an asymmetric key to validate the nonce. That cannot be spoofed. Other requirements that we need to have also, the things that are mandatory. Bearer tokens are access tokens that can be used by any party that possesses them without proving the possession of a cryptographic key. So they are simple and convenient, but also vulnerable to attacks that we discussed, such as token interception, token replay, and token redirect. It is important to follow the guidelines to ensure the security and integrity of the bearer tokens. TLS is mandatory for all communication involving bearer tokens, and TLS is basically, common, so that has to be used. And TLS protects the bearer token from being exposed or modified by an unauthorized party during transit. It also prevents man-in-the-middle attack, where an attacker intercepts and alters the message between the client and the server. To use TLS effectively, both the client and the server need to validate the certificate and certificate chains of each other. This is to ensure that they are communicating with the intended party. It is also best practice to avoid storing bearer token in cookies. Cookies are the information kept in the browser. This way, does not get compromised by another application in the browser. Cookies are often used to maintain state. You shouldn't be using it to maintain state. They're not suitable to attach the bearer token to be kept in the browser. This is because cookies can be easily accessed or manipulated by scripts or third-party domains, which can lead to token leakage or theft. Cookies can be vulnerable to cross-site requests, forgery attacks, where an attacker tricks the user into sending a forged request to a server with their cookie attached without their knowledge or consent. Scoping an audience is also a critical piece, like we discussed, for bearer token. It is very recommended and has to be followed. Scoping an audience or parameters indicate the intended use and destination of the bearer token. It defines the level of access and permission that the bearer token grants to the client. Maybe it could be read, write, or delete. Audience defines the resource server or service that the bearer token is intended for, such as photo, video, payment, things like that, indicating the intended use for the application. The scoping and audience lets the authorization server issue fine-grained and specific tokens to the client and to the resource server. This way, the resource server can verify if the token matches the requested resource. This would prevent unauthorized access or misuse of the bearer token by malicious parties, like we discussed. Finally, it's advisable to issue limited lifetime token. Limited lifetime tokens are tokens that expire after a certain period of time or after a certain number of uses. This is also very best practice. The authorization server can reduce the risk of token replay or token redirect attacks, where an attacker uses redirect a stolen token because the lifetime expires frequently. This would reduce the possibility of theft. The application can request a new token or refresh an existing token when needed. We'll talk about the refresh tokens. Those are basically some of the requirements and best practices that you need to have in place for OAuth 2.0 to be secure and cannot be used maliciously by bad actors. We will talk more in the next lecture. Hello, in this lecture, we will discuss refresh tokens. A client begins by acquiring both an access token and a refresh token through the authorization code grant flow that we discussed in previous lectures. This is the process that gets the grant, and then from the grant gets the access code from the authorization server. These tokens are crucial for interacting with protected resources. The access token is utilized for accessing protected resources hosted on the resource server. It is sent in the request's authorization header, like we discussed in the bearer token scheme. However, it's important to note that access tokens are temporary and expire after a set period of time, typically around 30 to 60 minutes. Upon expiration, any attempt to access protected resources with the expired token will result in a 4.1 unauthorized status message, like we discussed in a previous lecture, the www authenticate form, which would need to trigger the process for a new access token. However, this is where the refresh token, instead of the user going through the process of getting a grant from the user again and exchanging the grant to an access token, the client can use the refresh token to request a new access token from the authorization server. This would allow the client to maintain access without needing to re-authenticate and get an authorization grant again from the user. So it's crucial to understand that the refresh token itself plays a role in maintaining a longer connectivity, but minimizes the possibility of exposing the access token, because the access token is meant to be short-lived, but the refresh token can keep that authorization going for a while. Typically, the refresh token lifetime is around, it could be a month, right? If a client attempts to use an expired refresh token, the authorization server will return an error, which would necessitate a complete restart of the authorization process. While the refresh token does represent the authorization granted to the client by the user and aids in prolonging access, it is not an indefinite pass. The authorization server holds the authority to revoke or expire the refresh token at any time, ensuring security and control over the access to protected resources. We will discuss more in the next lecture. In this lecture, we will explore the client registration as well as client types and profiles. We will first talk about the registration process. The client is the application that requests access to protected resources on behalf of the resource owner. The client registers with the authorization server by providing its client type, redirection URIs, and other metadata. The client receives a client identifier and optionally a client secret from the authorization server after successful registration. The authorization server is the entity that issues access tokens to the client after successfully authenticating the resource owner and obtaining authorization, like we discussed previously. The authorization server provides a client registration endpoint for the client to register itself. The authorization server validates the client metadata and assigns a client identifier and optionally a client secret to the client. The authorization server may also revoke or update the client registration information at any time. There are distinct client types defined in OAuth, particularly focusing on how they authenticate securely with the authorization server. First, we have confidential clients. These are clients that are capable of keeping their credentials safe and secure. Think of a client implemented on a secure server where access to its credential is heavily restricted. These clients can also securely authenticate themselves through other means. On the other hand, we have public clients. These are clients that are not able to keep their credentials confidential. Examples including application running directly on the user's device. It could be a native application or web browser application. They also cannot securely authenticate themselves through any other means. It's crucial to understand that the classification into confidential or public depends on the authorization server's own criteria for secure authentication and its tolerance for exposure of client credentials. Importantly, the authorization server should not make assumptions about the client type. A client could be a combination of components, each with a different type and level of security. In cases where the authorization server doesn't support multi-component clients or doesn't provide registration guidance, each component should be registered as a separate client. We will take a look at some clients' profiles outlined here. The web application type client. This is a confidential client that runs on a web server. User interacts with it via web interface, but all the credentials and tokens are stored securely on the server away from the user's reach. And then we have the user agent-based application. This is a public client where the code is downloaded and runs within the user browser. With this setup allows for seamless integration with the browser capabilities during authorization. It also means that the credentials and protocol data are easily accessible by the user. And then you have native application. This is another type of public client, but this one is installed and runs directly on the user's device. The user can access the credentials and protocol data, and that dynamically issued tokens like access and refresh tokens are still provided reasonable level of protection, especially from potentially malicious servers. From the endpoints perspective, there are different endpoints. The authorization process utilizes two authorization server endpoints. Authorization endpoint, this is used by the client to obtain authorization from the resource owner via user agent redirection. And then we have a token endpoint. The token endpoint is used by the client to exchange an authorization grant for an access token, typically with client authentication. Then we have the client endpoint. On the client side, we have the redirection endpoint. This is used by the authorization server to return responses containing authorization credentials to the client via the resource owner user agent. The authorization endpoint plays a crucial role as it interacts directly with the resource owner or the end user to obtain an authorization grant. The authorization server has a responsibility to verify the identity of the resource owner, the end user. It is important to note that the specific methods used for this authentication, which could range from username and password, login, MFA, those are left up to the authorization server implementation, but we're talking about main authorization type servers that you have Google, Microsoft, and all those implement high level of security. Now, how does a client find, an application? Let's say if the user tries to authenticate, how does the client find the authorization endpoint? It is actually, there's an implementation in Oauth 2.0 that provides a mechanism for service discovery, which means that the client applications can dynamically discover important details about the OAuth authorization server, the location of the authorization and token endpoint based on registration information or service discovery. The authorization endpoint in Oauth 2.0 plays a crucial role in the authorization grant process. It serves as the interaction point between the resource owner, usually the end user, and the authorization server. When a client or application wishes to request access to protected resources on behalf of a user, it directs the user to the authorization endpoint. Here, the user is authenticated, they prove their identity, and they get asked to grant or deny the client access request. If the user grants permission, the authorization endpoint responds with an authorization code, which the client can then exchange for an access token at the token endpoint. This whole process ensures that the user's credentials remain secure, as they are never shared directly with the client. Instead, the client is given an authorization code that proves the user consent. The use of authorization endpoint in this way helps maintain security and user control in Oauth 2.0, a delegated access system. Now, the endpoint URI or web address can have extra information attached to it, formatted in a specific way called application xwww URL encoded, which we saw in the previous lecture. Security is paramount when dealing with user authentication, and the transmission of clear text credentials is not allowed. That's why when requests are made to the authorization endpoint, the authorization server must enforce the use of TLS to ensure a secure communication channel. If there are parameters sent without any values, the server behaves as if these were completely omitted from the request. Now, the redirection endpoint plays a pivotal role in the OAuth authorization process, particularly in the context of user redirection and callbacks. Callbacks happens after the resource owner, typically the user, interacts with the authorization server to grant or deny access to the client. The authorization server needs to communicate the result back to the client. So the authorization server redirects the user back to the client application. This redirection is to a specific URL set up by the client, known as the redirection endpoint. This is actually known by the authorization server during the client registration process. To ensure this redirection endpoint doesn't get spoofed or intercepted, the client must have previously registered this redirection endpoint with the authorization server. This is typically done with the registration process, like we said. The redirection includes important information about the authorization result, such as the authorization code, if the user was granted access, or error information if they didn't, and that's why it has to be TLS protected. To reiterate, the redirection endpoint is a URI on the client application that receives the authorization response from the authorization server. It is used to complete the authorization process and obtain the authorization code or access token, depending on the grant type. The token endpoint is used by the client to obtain an access token by presenting its authorization grant that was received from the user, or refresh token. The authorization endpoint and the token endpoint are both part of the authorization server in Oauth 2.0. The interaction between the client and the authorization endpoint and the token endpoint depends on the grant type used by the client. We discussed the grant types in previous lecture, which are authorization codes, implicit, client credential, or resource owner password. The token endpoint is used by the client to obtain an access token by presenting its authorization grant or refresh token. Now, again, the TLS is mandatory for confidentiality and integrity. and this basically kind of showed us the actual process where the end user tries to access a resource. They get redirected back to the resource owner for approval. They get the authorization code. The authorization code is sent to the token endpoint to exchange it for an access token, which in turn is used to receive access to get access to the resource. We will discuss more in the next lecture. In this lecture, we will explore intricacies of authorization for client and understand the mechanism of redirection and its importance in the OAuth process. Client authentication is a fundamental part of the OAuth 2.0 protocol. It ensures that only legitimate and authorized clients can request access tokens, which in turn grants them access to protected resources. Client credentials. These are the primary means of authenticating a client. A client is an application that acts on behalf of the user. They usually comprise client ID, which is a public identifier for the client. It includes also as well client secret, which is a confidential secret known only to the client and the authorization server. As far as authenticating the client, there are a couple of methods. The HTTP basic authentication scheme is the recommended method. In this method, the client ID and secret are concatenated with the colon, then base 64 encoded. This encoded string is then provided in the authorization header of the request. The other method is a request body parameter. This is an alternative method, but not as secure. The client credentials are included directly in the request body using client ID and client secret parameters. This method is not the first choice due to potential security concerns and should be used cautiously. There are also another method using asymmetric public-private key, which is not the topic of our discussion so far. For example, this is a request to refresh an access token using the request body parameter, which includes the client secret and client ID base 64 encoded. And we see here the content type says application/x www form URL encoded. This is the content type that is going to be showing in the header. The authorization endpoint on the authorization server must be TLS protected. In the response type of code, the client receives an authorization code, which is a temporary credential that can be exchanged for an access token at the token endpoint. In the response type of token, the client receives an access token directly from the authorization endpoint. Another response type is of registered extension. It covers a use case we didn't cover yet, which includes SAML. The redirection endpoint is a URI on the client application that receives the authorization response from the authorization server. It is used to complete the authorization process and obtain the authorization code or access token depending on the grant type. This flow is an example of the implicit grant. This is the implicit grant example use case. In this use case, the redirect URI will actually be used to relay the access token. So that's why TLS is important. So the URI registered by the client is actually the URI that would receive the token that would be used to access the resource. Here the client extracts the token from the redirect of the URL and turn around the token to use with an access protected resource. In this case of authorization code, this is the case of authorization code grant. In this case, the client URI and callbacks play a role in obtaining the access token from the authorization server. The client URI is the endpoint where the user is redirected after authenticating and consenting to the authorization request. The callback is the function that handles the response from the authorization server, which includes an authorization code. The client then uses this code to request an access token from the token endpoint. using its client ID and secret as credentials. So the state and audience parameters are optional, but recommended for security and validation purposes. The state parameter is a random string that the client generates and sends it in the authorization request, and then verifies it in the callback response to prevent CSRF attacks. In this case here, we see the state is equal XYZ, and that's also used to correlate back the authorization server, coming back with that redirect with the access token. The authorization server can support dynamic configuration of multiple redirection. This can be used for multiple redirection URIs that could be significant for the client to do different things. You can also register the client can register a wildcard domain, which is not recommended, but it can be done. This is an example: https://example.com/redirect as the redirect URI, and then they can use any subdomain in the authorization request, such as client.example.com, for example. The authorization server will compare the registered and requested redirection URIs by matching the scheme, the host, and the port component using exact string comparison, and the path component using case-sensitive string comparison. The query and fragment components are ignored when comparing URIs. This way, the authorization server can validate the redirection URI and avoid open redirect attacks. This method is not recommended by the specification, as it increases the likelihood of leakage of authorization code. Now, in Google Auth, for example, allows up to 100 redirect URI per client, and Microsoft Entra up to 256. The token endpoint is used by the client to obtain an access token by presenting its authorization grant or refresh token. The token endpoint is used with every authorization grant except for the implicit grant type. We will discuss more in the next lecture. In this lecture, we will further clarify authorization server endpoints, understand some miscellaneous topic as well. The authorization server has two main endpoints, the token and authorization endpoints. To recap, the roles for the authorization endpoint is to interact with the resource owner, this is the end user. It will be the endpoint that receives the consent granting the client access by the end user. The token endpoint will be used to exchange the authorization grant with an access token. From a functionality perspective, authentication and authorization servers are not necessarily the same. The authentication server verifies the end user identity, and in case of interacting with the application client, it can be the entity that issues the credentials to the client itself. The authorization token issues tokens. In the case of Google, for example, authentication is done by accounts.google.com, while authorization is done using www.googleapis.com. Sorry to keep harping on this issue, but it's important to understand this very clearly. The user tries to access the application, which needs access to a resource owned by the end user. The client doesn't have access to the resource, so it redirects the user to the authentication server, and it will provide it its own client ID and response type, code, or grant. The user is then redirected to the authorization server and to ask the end user if the end user authorizes access by the client. The end user then grants the request for the client to access his resources. The redirect message will be sent to the client, and here the redirect URI will be the one that was registered to the authorization server by the client. End user gets the redirect message with either code in case of implicit grant or token and state in case of authorization grant. Client will exchange this for a token. This is the last two arrows. The last two arrows is only if the code returned is of type token. This is for the authorization grant flow. It will exchange the token for an access token. This is an example of an access token response. We see here the content is application JSON and the parameter is no cache, just letting devices know that it shouldn't be cached. Now, sometimes there's going to be error responses if the request is missing. So for example, in case of an error, the authorization server would send the error code, and the error code could be something like invalid request. In this case, the request is missing the required parameter. Unauthorized client. In this case, the client is not authorized to request an authorization code using this method. Access denied. Maybe the resource owner, the end user, or authorization server denied the request. Unsupported response type. Maybe authorization server does not support obtaining authorization code using the method requested by the client. Invalid scope. This could be that the requested scope is invalid, unknown, or malformed. We also have server error. The authorization server encountered an unexpected condition that prevented it from fulfilling the request. Okay, then you have internal server error, and then temporarily unavailable. So there's a list of error codes that the authorization server will provide to the client to let them know that something happened wrong. And there's also error human readable form that can be sent to the client for it to know exactly what happened. So those are all things that enables the troubleshooting of those protocols. In this use case, username and password is exchanged. So this is the resource owner credential flow. We talked about it a couple of lectures back. In this use case, we see here the username and password is actually exchanged and sent to the authorization server. The resource owner provides the client with the username and password. Obviously, that's not secure, but this is one of the flows. The client requests an access token from the authorization server's token endpoint by including the credentials received from the end user, the resource owner. When making the request, the client authenticates with the authorization server. The authorization server authenticates the client and validates the resource owner credentials, and if valid, issues an access token. This also shows the post of the user credential and the corresponding response from the authorization server with the token. In the case of the client credential use case, the client authenticates with the authorization server and requests an access token from the token endpoint. The authorization server authenticates the client, and if valid, issues an access token. Like we see here on the headers, we see headers for the authorization. Well, here the authorization is basic, and this would basically concatenate the client secret and the client ID and client secret, like we discussed in the last lecture. This is another example. It's one example of extension is SAML extension, which we haven't talked about SAML, but SAML integrates with the OAuth process. And this is an example of the authentication grant. And in the case of SAML, it has additional things like assertion and other components. So we will talk more in the next lecture. In this lecture, we will cover OAuth PKCE. OAuth PKCE is an extension to the OAuth 2.0 authorization code flow that adds an extra layer of security for public clients. Public clients are applications that cannot keep a client secret confidential, such as native applications or single-page apps. Some example of public client in OAuth 2.0 are native applications that run on devices such as desktops, laptops, smartphones, or tablets. These applications cannot keep a client secret confidential as they are distributed to end users who can inspect or modify the application code. For example, a mobile app that uses OAuth 2.0 to access a web service on behalf of the user is a public client. Also, a single-page application that runs in a web browser and use JavaScript to communicate with the authorization server and the protected resource. These applications also cannot keep a client secret confidential, as they are executed in a browser environment where the source code and the network traffic are visible to the end user or other parties. For example, a web app that uses OAuth 2.0 to access users' Google Drive files is a public client. Some vulnerabilities that exploited the public client scenarios are authorization code interception attack. This is an attack where an attacker intercepts the authorization code returned from the authorization server. Some vulnerabilities that exploited the public client scenarios are authorization code interception attack. This is an attack where an attacker intercepts the authorization code returned from the authorization server to the public client within a communication path not protected by TLS, such as inter-application communication. This is communication within the client's operating system. The attacker can then use the authorization code to obtain the access code and access the protected resource on behalf of the user. This attack can be prevented by using the proof key for code exchange extension, which requires the public client to generate a random code verifier and derive a code challenge from it and send that code challenge along with the authorization request and the access token request, respectively. The authorization server can then verify that the code challenge matches the code verifier and that the authorization code was issued to the same public client. Another issue with this type of public client is the cross-site request forgery. The cross-site request forgery is an attack where an attacker tricks a user into visiting a malicious website that sends an unauthorized request to the authorization server using the user's browser session. The request can either initiate an authorization flow or use an existing authorization code or access token to access the protected resource. The attacker can obtain or misuse the user's credential or data. This attack can be prevented also by using a state parameter, which is a random value generated by the public client and sent along with the authorization request. The authorization server will return the same state value in the authorization request and authorization response, and the public client can then verify that it matches the original state value and that the response was intended for it. This is how the code interception works. Public client sends an authorization request to the browser or operating system specifying a redirection URI. The browser or operating system forwards the authorization request to the authorization server via TLS. The authorization server responds with an authorization code to the browser or operating system after authenticating the resource owner, the end user, and obtaining their consent. Now, the browser operating system returns the authorization code to the public client via redirection endpoint URI. The attacker intercepts the authorization code within the communication path that is not protected by TLS, such as intercommunication between their internal applications, which is easy to do. So this is within the client's operating system, sometimes not protected by TLS. Once they capture that authorization code, the attacker uses the authorization code to request an access token from the authorization server. This is an example of an actual vulnerability that exploited this issue concerning an Instagram application. The attacker created a malicious link that contains a logic flaw in the Instagram OAuth 2.0 implementation. The flaw allows the attacker to use their own client ID instead of the user's client ID when initiating the login flow with Instagram. The client ID is a unique identifier that is assigned to each application that uses OAuth 2.0 to access Instagram. The malicious link also specifies the malicious website as the redirection URI, endpoint URI, where the attacker can receive the authorization code from Instagram. So the attacker basically sends a malicious link to the user via email or message, pretending to be a legitimate source, such as a friend or a follower. The user clicks on the malicious link, trusting the sender or the appearance of the link. The user's browser or operating system visits the malicious website that is controlled by the attacker. The malicious website redirects the user's browser or operating system to the Instagram login page, where the user can authorize the attacker's application to access their Instagram account, but they are not aware that they are authorizing the fake application. The redirection includes the attacker's client ID instead of the user's client ID, which is a violation of the OAuth 2.0 specification. The user's browser or operating system logs in with the user's credential, either automatically or manually, and grants permissions to the attacker's application. Instagram returns an authorization code and a state value to the user's browser or operating system, which can be used to obtain an access token from Facebook. The authorization code and the state value are appended to the redirection endpoint URI that was specified by the attacker in the initial request. So the user browser or operating system redirects to the malicious website again, which now receives the authorization code and the state value from Instagram. The attacker can then use them to request an access token from Facebook. The malicious website sends an authorization code and the state value to the attacker, who can then use them to request an access token from Facebook. The attacker requests an access token from Facebook using the authorization code, the state value, and the user's client ID. The user's client ID is obtained by intercepting or guessing it from other sources. Facebook does not validate that the client ID matches the one that was used to initiate the login flow with Instagram, which is also another violation of the OAuth 2.0 specification. Facebook returns an access token to the attacker, which can then be used to access the user's account on Instagram. The attacker uses the access token to access or misuse the user account on Instagram, such as posting, deleting, or modifying content that happened with Instagram, using OAuth with Facebook. We will discuss more in the next lecture. In this lecture, we will talk about another issue relating to the public client. Another issue is cross-site request forgery, which can happen as follows. The public client sends an authorization request to the browser or operating system, including the state parameter that is a random value generated by the public client. The browser or operating system forwards that authorization request to the authorization server via TLS. The authorization server responds with an authorization code and the same state value to the browser or operating system after authenticating the resource owner and obtaining their consent. The browser or operating system returns the authorization code and the same state value to the public client via the redirection endpoint URI, which we explained in the previous lectures. The public client sends an access token request to the authorization server, including the authorization code and the same state value. The authorization server validates the state value and the authorization code and responds with an access token and the same state value to the public client. So in this case, the attacker sends a malicious link to the user, which leads to a malicious website that is controlled by the attacker. The user visits the malicious link in their browser or operating system without knowing that this is malicious. The malicious website sends an unauthorized request to the authorization server using the user's browser session, which may contain cookies or other credentials. The request can either initiate a new authorization flow or use an existing authorization code or access token to access the protected resource. The browser or operating system forwards that unauthorized request to the authorization server via TLS. The authorization server responds with an unauthorized response to the browser or operating system, which may contain a new authorization code or an existing access token. Depending on the type of request, the response may not include the state value as it was not sent by the public client. So the browser or operating system returns the unauthorized response to the malicious website, which may contain a new authorization code or an existing access token. The attacker can then use them to obtain or misuse the user's credential or data. This is an example of a vulnerability that exploited a TikTok app. The attacker creates a malicious link that contains a JavaScript payload that can perform a cross-site request forgery attack on the TikTok carriers portal. The payload also injects the malicious link into the next URL parameter of the TikTok SSO endpoint, which is an open redirect vulnerability. The attacker sends the malicious link to the user via email or message pretending to be a legitimate source, such as a recruiter or friend. The user clicks on the malicious link, trusting the sender or the appearance of the link. The user's browser or operating system visits the malicious website that is controlled by the attacker. The malicious website executes the JavaScript payload in the user's browser or operating system, which initiates a cross-site request forgery request to the TikTok carriers portal. The request starts the SSO process with Facebook using the user's existing browser session or cookies. The request also includes the next URL parameter that contains the malicious link now. The user's browser or operating system send the cross-site request forgery request to the TikTok carrier portal, which does not have any cross-site request forgery protection and accepts the request as valid. The TikTok carriers portal redirects the user browser or operating system to the Facebook login page where the user can authorize TikTok to access their Facebook account. The user's browser or operating system logs in with the user's credential either automatically or manually and grants permission to TikTok. Facebook returns an authorization code and a state value to the user's browser or operating system, which can be used to obtain an access token from Facebook. The authorization code and the state value are appended to the redirection endpoint URI that was specified by TikTok in the initial request. Now, the user browser or operating system sends that authorization code and state value to the TikTok carrier portal, which validates them and issues an access token for the user's account. The access token is also appended to the next URL parameter that was specified by the attacker in the initial request. The TikTok carrier portal redirects the user's browser or operating system to the next URL parameter, which is not validated by TikTok and contains the malicious link. The redirection also includes the authorization code, state value, and the access token as a query parameter. The user's browser or operating system redirects to the malicious website again, which now receives the authorization code, the state value, and the access token from TikTok. The attacker can then use them to access or misuse the user's account on TikTok. We will discuss more in the next lecture. The PKCE consists of the following. The client sends an authorization request to the authorization server, including a code challenge. This code challenge parameter is derived from a randomly generated code verifier. The authorization server responds with an authorization code to the client after authenticating the resource owner and obtaining their consent. The client sends an access token request to the authorization server, including the authorization code and the original code verifier. The authorization server validates the code verifier and the authorization code and responds with an access token to the client. The client now uses the access token to request a protected resource from the resource server. The resource server validates the access token and responds with the protected resource to the client. By using PKCE, Instagram vulnerability could have prevented the attacker from obtaining an access token with just the authorization code, as they would not have access to the code verifier. This code verifier was generated by the user's client. The attacker would also not be able to generate their own code verifier and code challenge, as they would not match with the ones stored by Instagram. Therefore, the PKCE could have added an extra layer of security to the OAuth 2.0 authorization code flow and made it more resilient against authorization code interception attacks. This diagram, although it's busy, it shows the steps that happen. The user clicks on a legitimate link from the client, which is the app that wants to access Instagram. The link initiates the OAuth 2.0 authorization code flow with PKCE. The user's browser or operating system sends an authorization request to Instagram, including a code challenge parameter that is derived from a randomly generated code verifier. The code verifier is kept secret by the client and not sent at this point. So Instagram redirects the user's browser or operating system to the Facebook login page, where the user can authorize the client to access their Instagram account. The user's browser or operating system logs in with the user's credential on Facebook, either automatically or manually, and grants permission to the client. Facebook returns an authorization code and a state value to the user's browser or operating system, which can be used to obtain an access token from Facebook. The authorization code and the state value are appended to the redirection endpoint URI that was specified by the client in the initial request. So now the user's browser or operating system sends the authorization code and the state value to Instagram, which validates them and issue an access token for the user's account. The access token is also appended to the redirection endpoint URI that was specified by the client in the initial request. So Instagram redirects the user's browser or operating system to the client, which receives the authorization code and the state value from Instagram. The user's browser or operating system returns the authorization code and the state value to the user, who can then use them to request an access token from Instagram. The user sends an access token request to Instagram, including the authorization code, the state value, and the original code verifier that was generated by the client. The user's browser or operating system sends an access token request to Instagram, including the authorization code, the state value, and the original code verifier that was generated by the client. Instagram validates the authorization code, the state value, and the code verifier with Facebook using a one-way function, such as a SHA-256. If they match, it means that the client is the same party that initiated the login flow and received the authorization code, and Instagram requests an access token from Facebook. If they do not match, it means that there is a mismatch between the parties and Instagram rejects the request. Facebook returns an access token to Instagram, which can be used to access the user's account on Instagram. Instagram returns an access token to the user's browser or operating system, which can be used by the client to access or use the user's account on Instagram. The attacker creates a malicious link that contains a logic flaw in the Instagram OAuth 2.0 implementation. The flaw allows the attacker to use their own client ID instead of the user's client ID when initiating the login flow with Instagram. The client ID is a unique identifier that is assigned to each application that uses OAuth 2.0 to access Instagram. The malicious link also specifies the malicious website as the redirection endpoint URI, where the attacker can receive the authorization code from Instagram. The attacker sends the malicious link to the user via email or message, pretending to be a legitimate source such as friend or follower. The user clicks on the malicious link, trusting the sender or the appearance of the link. The user's browser or operating system visits the malicious website that is controlled by the attacker. The malicious website redirects the user's browser to the operating system or the operating system to the Instagram login page, where the user can authorize the attacker's application to access their Instagram account. The redirection includes the attacker's client ID instead of the user's client ID, which is a violation of the OAuth 2.0 specification. The user's browser or operating system logs in with the user's credential either automatically or manually and grants permission to the attacker's application. Instagram returns an authorization code and a state value to the user's browser or operating system, which can be used to obtain an access token from Facebook. The authorization code and the state value are appended to the redirection endpoint URI that was specified by the attacker in the initial request. The user's browser or operating system redirects to the malicious website again, which now receives the authorization code and the state value from Instagram. The attacker can then use them to request an access token from Facebook. The malicious website sends the authorization code and the state value to the attacker, who can then use them to request an access token from Facebook. The attacker requests an access token from Facebook using the authorization code, the state value, and the user's client ID. The user's client ID is obtained by intercepting or guessing it from other sources. Facebook does not validate that the client ID matches the one that was used to initiate the login flow with Instagram, which is another violation of the OAuth 2.0 specification. Facebook rejects the access token request from the attacker as it detects a mismatch between the code challenge and the code verifier. The code challenge is derived from the code verifier that was generated by the user's client, while the code verifier is provided by the attacker. Therefore, Facebook can tell that there is an authorized code interception attack and deny access to the attacker. The person who discovered this vulnerability actually got $30,000 as a bug bounty from Facebook. So we will talk more in the next lecture.